for the introduction. Hi everybody, I'm Chun from Chun University. It's my pleasure to present our work about lip interact, which is an interaction technique that enables users to access functionalities on a smartphone by issuing silent speech commands. Lip interact relies on the device's front-facing camera to capture the user's mouth while using the device and recognize lip movements into commands through computer vision technology. For example, with lip interact, a user, that is me, can simply mouth the verbal command screenshot to directly take a screenshot within one step, even with one hand. Also, while typing with fingers, a user may prefer to use lip interact for fast text editing, such as copy-paste, highlight, undo, redo, adjusting the cursor, etc. This achieves more fluent input experience. So first of all, why do we want silent speech interaction? Touch interaction on smartphone is very intuitive and simple, but given the limited screen size and the hierarchy UI layouts, reaching a desired item often requires a series of operations, such as slidings and clickings to jump from one page to another. So it would be greater if we can access functionalities in a more rapid way. And researchers have been trying to achieve this by augmenting the device's input ability. Although they may have different appearances and hardwares, the interaction principle behind is to use gestures. While gestures can be very useful on smaller command sites, it has several limitations in actual use, in many actual use, such as the good gesture designing, the scalability of the gesture set, and the cost of gesture learning and memorizing. A successful alternative is voice input, which has been being integrated onto modern smartphones. Users can instruct the phone to open apps and access specific settings without touching the screen. Voice input offers rich expressivity because it is based on the natural language, so that it can avoid many limitations of the conventional gesture input, as mentioned above. However, not all users like it, and people around me hardly use voice input. They're concerned about privacy issues and social norms, especially in public settings. So how about we just keep the form of voice interaction, but actually not vocalize any sound? In this way, the user can access functionalities in a more rapid way, just like using voice interaction, and at the same time, since we don't have to really vocalize the sound, we expect that lip interact can largely alleviate the issues surrounding social norms. And it is worth noting that the concept of silent speech is not new, and many works have explored silent speech interfaces, such as the latest one, the silent voice by Dr. Masaki, which has been presented on Monday. However, these prior works mostly use an invasive setup, adding additional sensors on actual devices, which probably impedes the scalability of these solutions in real-world scenarios. Well, the front-facing camera on smartphone is a natural sensor that can capture, our head and mouth when we are using the device. So we deem this to be a very promising setup in practical use. Now back to our technique. We now describe the system designs and implementation details. For lip interact, there are several very basic but practical questions. How far and how many commands can lip interact support? And how about the recognition accuracy? Is it really usable? So first, the command silently spoken by the user must be recognized very accurately and robustly, because a false positive in mobile interaction can be very annoying to users and requires very heavy effort to recover it. For lip interact, we certainly hope that the system can recognize whatever the user says through silent speech, but this seems impossible because silent speech recognition has intrinsic limitations. First, several phonemes often look the same, which means a series of mouth movements may correspond to many different pronunciations. This leads to a very low recognition accuracy in sentence lip reading even with the modern state-of-the-art machine learning methods. And this is unusable for an interactive input system. Second, in everyday speaking, we may do very little or even no mouth movements so that the amount of information may be not sufficient for recognition. That exacerbates the problem of the low recognition accuracy. So since these two problems cannot be solved technically, we can avoid them through several interaction designs. And accordingly, we add two design constraints. First, lip interact only considers short and visually distinguishable commands rather than long sentences, such as those in a conversational system. And second, users are instructed to issue commands in a more standard way than they are currently talking. But please note that the exaggeration is still within a normal range of speaking. Users only need to mouth the command by thinking that their lip movement can present each syllable clearly. So overall, these two constraints is a kind of trade-off between the naturality and the usability of the technique. And another design is that lip interact, which is our system, is context-aware. The system identifies the current state and uses the corresponding model to recognize user's input. The user is allowed at any time to access universal system functionalities such as home, back, screenshot, etc., and can access specific features in current applications. So when we were doing this work, before we wrote this paper, to realize the prototype, we equipped a smartphone with a camera at the top, and the camera was connected to a computer running the image processing and neural network classifier. At that time, this setup afforded us a flexible framework for faster prototyping. But now we have realized the lip interact on self-contained smartphone without any additional computing resource. I will talk about this later and give a short live demo. So for the command side, we used standard Chinese as the experiment language to facilitate data collection and user evaluation in our local area. But I think the results can be generalized to other languages. In this work, we cannot cover all the functionalities on smartphone because of their large quantity, especially the built-in features in various apps. So to validate the feasibility of our system, we selected 44 typical commands through a user elicitation study. Based on the mechanism of context-aware functionality support, the 44 commands include 10 frequently used system settings. Sorry for the confusion if you don't understand the Chinese characters. You can see the English below. And also include 10 most popular apps, 6 most frequently used operations to handle up pop-up windows, and 18 built-in features for 2 representative apps, WeChat and Notepad. And now is the recognition part. In each frame, we use the method from that paper to identify the facial landmarks, and 20 of them describe the feature points of the mouth. Based on these solutions, a fine transformation is applied to extract a multi-crop image for each frame. And then what we need to do is segment the mouth image sequence to decide whether the user is issuing commands or not. A sliding window algorithm is used to detect and transfer between these 4 states, begin to silently speak, continue speaking, stop speaking, and other states. We calculate statistical features of the mouth opening degree and use a decision tree to decide whether or not to remain in the current state or move to the next. So what we need to do then is just get the sequence of the mouth images from the begin to speak state to the stop speaking state and recognize them into a command. This figure shows the architecture of the recognition model. It refers to the latest work on lip reading in computer vision and was improved to adapt to lip interactive mobile interactions. It is an end-to-end deep learning model that consists of many 3 parts. The model starts with a spatial transformer network on each input frame of the sequence. So what is the spatial transformer network? The spatial transformer network was proposed in 2015. It is a learnable module that has the ability to dynamically learn variance to image transformation and then spatially transform the feature maps. Intuitively, here are some examples in that paper at the bottom of this slide, and we can see it as a kind of image normalization, and it has been tested to help improve the recognition accuracy. In our scenarios of lip interact, the orientation between the user and the camera may vary each time a command is issued. Of course, we hope that all the image sequences are like the left ones, but the most common cases are like the right ones, where the mouth have different relative orientations toward the camera. We use the spatial transformer network to solve this, to transform the image sequences to the left style one. Here is the result. We can see the transformation in the network learned the regular grid, and the transformation results on the right side. So the image now seems to have a very right direction. The rest of the network is very regular, following by 3 layers of CNN, 2 layers of RNN, and output to make classifications. And here are some cases from our one participant. So she is speaking Chinese, and so to examine the recognition accuracy of our system, we collected data from 22 participants, and after some data augmentation, we finally got at least 1,000 samples for a single command. So for training and evaluation, we divided the commands into 4 groups based on the principle of system functionality plus current context. Each group has about 20 commands. So we first do the leave one subject out cross-validation, which is a predictor of the performance when user uses lip interact for the first time. On average, the accuracy was over 95%, indicating that our system could accurately identify even a new user's commands. We then did a simulation to evaluate the recognition accuracy across time to simulate real-world scenarios when the pre-trained model improves as the number of users increases. And the results shows that the accuracy improved significantly and reached about 99% at the 6th update. And as I mentioned above, we have realized the lip interact on self-contained phone, and it is mostly based on TensorFlow Mobile. And now I'm trying to give a short demo. So hold on for a minute. So this is the mirroring of this smartphone, and often on the home screen, if we want to open an app, we set left to right to search and touch. For example, with lip interact now, if I want to open an app, for example, the browser, I just need to do this. And the browser is opened. And now if I want to go back to the home screen, I just say home, which in Chinese is like 桌面. You can look at my mouth. So it's back to the home screen. And if I want to open another app, WeChat is the largest app in China by active users. And Chinese people know this is WeChat. WeChat has a lot of built-in features. Often we need to tap the buttons and choose from menus to access them. And now if I want, in this app, I can directly access these features. For example, the moments, which is a kind of friend social feed, something like that. So it opens the social media, and if I want to pay something, in China, mobile pay is very popular, and I want to show my payment code. So it shows my code, and you can scan them now and transfer some money to me. And now if I want to send this picture to a friend of mine, I want to take a screenshot, right? And take screenshots, and it's very popular, but not very convenient. We have to slide down it or choose, or in Huawei phones you can knock. And now I just take a screenshot. Oh, it takes a screenshot. And thanks for the applause. I'm now finished. And okay, there is a little bit dark down there, and go outside. There should be light. And I want to open the flashlight, right? So I can say. Oh, sorry, it misclassified. It is normal, and I will try it again. Oh, it said can't turn on the flashlight. Camera light is being used by another app, which is the camera capture. But I have tested on other phones like Huawei and Xiaomi. It works. It can open the two camera at the same time. So this is a Samsung phone. Please try to use Chinese smartphones. So I have finished my demo, and the last slide I will go very quickly. What happened? We then conduct 2 user studies to evaluate the interaction performance of Leap Interact. The results are not surprising. Leap Interact is awesome to use, just like what I have done. And please to refer to the paper for more details. And of course, our system still has a lot of limitations and room for improvement. First, Leap Interact has using conditions. If you have a heavy beard, maybe this is not a good interaction technique for you. And there's a lot of work to do to improve the system performance, such as using the 3D camera for more robust recognition, reducing the latency, and increase the recognition accuracy by collecting more data. And it is also important to test silent speech on more languages. But personally, I am very optimistic about this technology to be generalized to our other languages. And our experience is that if you can distinguish the commands from your eyes, and the computer can make it. And thank you for your time, and I'm glad to take any questions.
So we don't have a lot of time for questions, but maybe one quick one. If you do a live demo, you get a bit of slack for time, so that's okay. Go ahead, one question.
Andrew from Google. So you mentioned about kind of the benefit is about the social norm part. Have you actually looked into how onlookers looking at people performing kind of like a silent command and how they perceive their kind of behavior? Because it doesn't attract attention, but when you are talking without any voice, actually it may perceive violating social norms.
Just as I said, we made a user study at the study 3 in a paper, and we compared silent speech interaction versus general speech interaction, and collect some subjective feedback from our participants. And our participants report that silent speech is more privacy, and it's less noticeable.
So do you have any insights on the people looking at those people performing silent speech, the participant performing?
Sorry?
So let's say I'm doing silent speech and looking at me. Do you have kind of like any insights on the people that are actually looking at the people?
Yeah. We test the two measures: the social norm measurement for the people using the device and other people standing by, and we have the data in the paper, and it looks like you are reading a spell.
Okay, cool.
Okay,
Thank you.
Great. We'll have to end it there. If you have any more questions, all our speakers will be at the front after the talk, so you can ask then. And let's thank our speaker one more time. Thanks.